And okay, good. All right, it's just about time to get started. And I guess I have to introduce myself as the first speaker. So I'm from the City College of the City University of New York, and I want to talk about a chemistry course for non-science majors. I put this course together after there was a request from the College of Liberal Arts and Sciences to add experiments to the non-majors course, which seemed to me entirely reasonable. But in the end, budget cuts cut out the lab part. However, I found a way to use it in any case. All right, it is now time to get started. Hopefully everybody is here who wants to be. And so we have a course for non-majors. We've always had a course for non-majors. The course is required, or 2 courses out of 4 are required for non-science majors. Most of these students are very poorly prepared in science and don't particularly want to take a science course. So why would they take such a science course? Well, this course has several aims, one of which, of course, is to teach the rudiments of chemistry. This is not something that excites the students that much. Now, the other thing that I wanted to get across was that that science is not true because A, the book says so, and B, the teacher says so. You actually have to do experiments. You have to learn, and you have to do some work to learn the material, to learn these facts that the book and the teacher repeat. But fundamentally, why should the student bother? They're not going to be a chemist. They're not going to be any kind of a scientist. So what's the course good for? What does it tell the student about the life they're going to live? What does it say about public policy, for example? Well, there the students should be engaged because they are going to have to vote at some point. They are going to have a voice in public policy. And that, in the end, is a critical part of the course. So I aimed the course to include climate change and ocean acidification, parts where chemistry plays a fundamental role, but the students generally would not know much about it, and where there was a great deal of misinformation being distributed by climate denialists and similar types. So I wrote this up, and it turned into a book, which is now out of print, I'm afraid. No, it's actually available still. And it has experiments in it. So the first thing is that you have to get across the idea that experiments are necessary in order to learn anything. There's a brief introduction, but not as brief as in many books. Many books have a half a page on what science is about, say a few platitudes, and go on. But I discussed this for several pages and introduced a vocabulary of discussions in science, the difference between theory and hypothesis, theory being well-established, hypothesis needing confirmation. I went through a little bit about Karl Popper and the necessity of doing experiments to disconfirm a hypothesis so that if it is not disconfirmed, then you can begin to believe it. If it's not disconfirmed often in enough experiments. Now, the first experiment was actually just done in class. Which line is longer? If you take 2 lines, they had to be perpendicular, otherwise you could judge by eye. And they measured them in 2 ways, one with a small coin and second with a millimeter ruler. The small coin, of course, gave very rough precision, and the millimeter ruler gave much better precision. This got across the idea of experimental error and the accuracy of measurement and the importance of using the correct instrumentation, primitive as this was, in order to get a measurement. So they actually got the idea of what it meant to take a measurement, and then they had to write a lab report about it, discussing whether the lines were equal within experimental error or not. There was a considerable discussion during the course about whether the experimental error or what experimental error actually meant. So the course went on to another experiment in class, and then to actual experiments in lab. But since there was no lab period, I had the department technicians do the experiments with several repetitions so that they would get some scatter. They were doing them with rather primitive instrumentation intentionally. We'll talk about that in a minute, so that there was some scatter. And the data were given to the students, who then had to do a lab report on each experiment. That replaced the term paper that's usually done in this course. So they had real experiments, they had a description and pictures of the apparatus, and it helped them to get an idea of what it was that it meant to say something was true or not true. Now, in the end, the point was to get to a discussion of public policy, and public policy that depended on chemistry in particular. So climate change was a natural choice. And the material that was covered in the class to get to climate change was somewhat different than the standard chemistry course. I included a section on thermodynamics. Since I usually teach physical chemistry, thermodynamics is a subject that I happen to like. But there was a qualitative discussion. Students had absolutely no numerical sense, and using algebra would have been too much. But you can go through thermodynamics qualitatively and get the general ideas across. I discussed black body radiation, which is almost never included in such a course. I did not discuss the formation of plastics, and I did not show them pictures of all the people who discovered different kinds of plastics, which I have seen in too many books. pH was covered in some detail because we included ocean acidification as one of the topics. And it was a natural addition to carbon dioxide in the atmosphere. So still, we had to get across the rudiments of chemistry. So we begin with the usual topics: atoms, molecules, covalent ionic polar bonding, and so on. And the experiments introduced obvious topics as well, starting with concentration. In fact, the first real lab experiment was first to essentially define molarity and then measure a concentration. Simple as this was, it sort of cemented the idea of concentration, which is critical for a discussion of pH and essentially everything else that we did. So they learned molarity and so on. Now, at the end of each section, there were review questions in the book, and so that they would, this is necessary in any book, really, so that they can test their knowledge and make sure that they understood what they were doing. The lab reports, of course, required answering questions as well. And there too, they reviewed and cemented their knowledge. So the students themselves were variable level. Some of them actually did know some science. Some of them had forgotten their junior high school arithmetic. There's a section in the book, about 3 or 4 pages, on logarithms and exponents. Hopefully most of the students didn't really need this, but I could not avoid using exponents in discussing pH. So I had to include this, and hopefully most of the students didn't really need this, but some of them definitely did. I did not spend class time on it. Now, the level of the experiments was pretty simple. The students, of course, had never used a balance. They'd never used lab glassware. And so we begin at the beginning. This is a figure that's taken from the book, in which it shows them how to read a graduated cylinder. As I said, you begin at the beginning with these students. Now, one experiment at the beginning was conservation of mass. And this was, again, a very simple experiment. They essentially weighed the barium chloride solution, the sodium sulfate solution, mixed them, got a precipitate, weighed them afterwards, and found that, in principle at least, the weight was the same with an experimental error. Again, experimental error is critical here. And when the techs ran the experiment, of course, it worked, and with reasonable scatter. Possibly if the students had done it, it would not have worked as well. But the point was that they saw in principle how you could test for conservation of mass. Of course, one would, in real life, one would do it to far greater accuracy, but here it was done simply. In fact, techniques that are no longer in use are sometimes conceptually more useful than modern instruments in that they are not a black box. Nobody would do an experiment with colorimetry anymore. In the 1950s, when I was a student, we actually did a colorimetry experiment. Now, of course, you would use a spectrophotometer. But to the students, the spectrophotometer would be a black box. Here,
Dr. Green, 1 minute. You have 1 minute left.
All right, 1 minute. Oh boy. Okay, so we got to climate change and ocean acidification. pH change is measured in an experiment, and they got the Keeling curve of carbon dioxide content. And the figure on the previous slide helps with understanding the importance of secondary gas as well. That slide is not here, but the absorption of light was included. And so conclusions, the students can be introduced to the basic ideas of obtaining information by experiment. The experiments improve the understanding, and they come away with an idea about the mechanism by which climate change occurs. It cannot be guaranteed that they will not fall prey to political denialism, but at least they have the basis for resisting it. Okay, there was also a chapter on nuclear energy, which we do not have time for. So thank you, and I hope if you have any questions, I will be happy to answer them. Thank you.